All right. Okay, let's study this property. Limit at infinity. Okay. Now a general question is: suppose we have a function. Question. Now suppose given a function f(x), we want to know what happens if the value of x. What happens if x value can be arbitrarily large? What happens to the function value if the x value can be arbitrarily large? Okay, so then find. Do we find that actually x approaches infinity f(x), this limit exists or not? Exists or not? I.e., the behavior of the function when the input x can be arbitrarily large. Okay, for instance, example, y equals fx, okay, to be 1 over x. Now, if you find its graph, plot its graph, raster particle. So it's 1 over x. This is the graph of 1 over x. Okay, y equal 1 over x. This is x. This is y. Now we have another branch. Okay, this is another branch. Then we have, you see, as x approaches infinity, the graph of y equal fx, 1 over x, gets arbitrarily close. Arbitrarily close to the x-axis. Okay. Now, in this situation, we call the x-axis a horizontal asymptote. To the graph of the function fx. Y equal fx. Okay, so this definition of horizontal asymptote. Okay. Then you see, if we do the numerical value, so this is the x, this is the 1 over x. Okay. Now you see, if x becomes, so if x is 1, then 1 over x is 1. If x is 10, 1 over x is actually 1 over 10, 0.1. If x is 100, 1 over x is 0.01. X is 1000, this is 0.00, 0.01. If x is 10,000, then 1 over x is 0.0001. You see, as x becomes arbitrarily large, so what happened to 1 over x is it becomes arbitrarily close to the number 0, okay, to the number 0. Then we see if a number gets arbitrarily close to 0, then in this case, we see this limit, you see, get arbitrarily close to 0. So the value of 1 over x get arbitrarily close to 0 as x get sufficiently close to, if x becomes sufficiently large, okay. In this case, we see 1 over x has limited 0. Definition. Okay, if the value of fx get arbitrarily close to 0, arbitrarily close to L, close to a number L, as x gets sufficiently close to a, close to a number a, then we see the limit of fx as, then we see the limit of fx as x approaches a, as x approaches what happened? Close. We want a actually to be infinity. If x is sufficiently large, the limit of fx is L as x approaches infinity. What we write is limit x approaches infinity, fx equals L. Okay. Okay. So if we plot a graph, suppose what is L? So this is L. Now limit of x, fx approaches L as x becomes arbitrarily large. So so y equal fx. So in this case, we have limit fx as x becomes infinity, approaches infinity. This limit is L. You see the graph of fx can get absolutely close to the line, horizontal line L. Okay. In this case, we have a horizontal asymptote. Which is the function y value to be L. Okay, y value to be L. Okay, example. A concrete example. Y equal arctan x. Okay. Now, this is the inverse of the tangent. Okay, this is the inverse of the tangent function. Okay. Now, if we plot the graph of tangent x, remember, how do we plot the tangent x? This is x. This is the y. Tangent x has a vertical asymptote. Okay, vertical asymptote. It's negative pi over 2 to pi over 2. Okay, so it looks like this manner. Okay, it looks like this manner. Okay, so this is y equal tangent x. Now, to plot arctan x, what we do is we flip x with y. Okay, we switch x with y. So we use symmetry, flip this graph with respect to y equal to x. Okay. So what we do is we flip x and y. Then the vertical asymptotes becomes now horizontal asymptotes. Okay, horizontal asymptote. Now it becomes this manner. Okay, it becomes this manner. Okay. So this is y equal arctan x. Okay. Now you see, as x approaches approaches infinity, you see, as x value becomes arbitrarily large, the y value actually approaches a number. Now this number is, by symmetry, it's actually pi over 2. Now this number is actually negative pi over 2. All right, so we have limit x approaches infinity, arctan x. This limit is actually pi over 2. Okay. It approaches pi over 2. Now, as x approaches negative infinity, now negative infinity is, we just switch the direction. Then we get a negative infinity. The definition of negative limit at negative infinity is the following. If the function value gets opposite close to L, if x get sufficiently large, but it's large negative, okay, negative large, then we see as the limit of fx is L as x approaches a negative infinity, okay. So what we write in this case is x approaches negative infinity, okay, arctan x. Then in this case we get this is actually by symmetry. This is all the functions. So this we get a negative power 2. Okay, negative power 2. Okay. Okay. Now what we a general thing to remember is this. Now if limit x approaches the infinity, x to some positive power r, this thing approaches infinity. Okay, this approaches infinity. R is positive number. R is positive number. Okay, for instance, example, square root of x, x becomes infinity. This is actually infinity. Okay, infinity. Now, if we do the rest, the y over z thing, reciprocal. So this is actually as x becomes large, the denominator becomes up to large. The numerator is fixed. So in this case, this is 1 over a large number. So you see this actually approaches 0. Can be after the small, okay, as x becomes large. So if you plot the table, for instance, x square root x, 1 over square root x. So for instance, if x is 100, square root x is 10, 1 over the thing is 0.1. If this is 10,000, x is 100. 1 over root x is 0.01. Now if it's 10 to the 6, a million, then this is 1,000. This is 1 over 1,000, 0.01. Now you see as x becomes large, so x approaches infinity, approaches large. So this number get approach close to the number 0. Okay. So in this case, we have limit 1 over root x as x approaches infinity is 0. Okay. Okay. Now when we do negative infinity, we need to be careful because x to some power r. Now if r is a rational number, for instance, if r is 1/2, then actually we need to take a square root. Okay. Then we need to take a square root. Then in this situation, now we need to be really careful because we don't want to take a square root of a negative number. Okay, we don't want to take a square root of a negative number. Okay, so then actually we know if x approaches negative, to avoid this situation, we use n to be integers. Okay, positive integers. Okay, for positive integers, then we don't have the issue of taking square root of a negative roots. Okay. All right. Z plus means this is positive integers. Okay, positive integers. Okay. Let's see some example. Okay, we do some infinite limit. X approaches infinity. X over x plus 1. Okay, if denominator and numerator, they both have x, they are both polynomials of x, what we do is we divide by the highest power of x. We divide it by the highest power of x, okay? So we do the algebra. So divide by every term, divide by the highest power. In this case, denominator and numerator, they are both degree 1, okay? So we divide by the highest degree, which is degree 1. Every term divided by x. Then x divided by x. So this we get x over x, we get 1. X over x, so we get 1. Y over x is 1 over x. Okay, limit x approaches infinity. Now use limit laws so we can distribute. Okay, 1 over 1 plus limit x approaches infinity 1 over x. And then use limit law 1 over x as x becomes arbitrarily large. Okay, then 1 over x get object close to 0. So this is 1 over 1, which is 1. Okay, so this actually tells us x and 1 over x, they differ by 1, but this difference is insignificant if x becomes arbitrarily large. Okay, x becomes arbitrarily large. So you see x value, for instance, x over x plus 1. If x is 9, so this is the x over 9 plus 1, so it's 9 over 10, so it's 0.9. If x is 99, then x over x plus 1 is 0.99. If x 999, this becomes 0.999. Okay, you see x gets arbitrarily close. X approaches infinity here. Now 1 over x, you see this number 0.9, 0.99, 0.999. So this number x over x plus 1. This approaches number 1. Okay. So in this case, we have horizontal asymptotes. Okay, we have horizontal asymptotes. Actually 1. Okay, y equal also horizontal. Then we have horizontal asymptote y equals to the y equal to 1. Okay, more examples. Okay, example. Okay, x squared over 3x squared plus 5. Now here the highest degree is degree 2. Okay, so we divide it by the highest degree, x squared. Okay, so this we divide by the highest degree. X squared divided by x squared, 3x squared divided by x squared, 5 divided by x squared. And then x squared divided by x squared, this is 1. 3x squared divided by 3x squared, so this is 3. And then use limit laws. Okay, now 5 over x squared. Oh, sorry. This is 1 over 3 plus limit x approaches infinity, 5 over x squared. 5 over x squared, x becomes absolutely large. 5 over x squared can be absolutely close to 0. So this limit is 0. So it's 1/3. You see, 1/3 is exactly the ratio of the highest coefficients. Okay, so 1 is the coefficient of x squared. 3 is the coefficient of x squared. Okay, so 1 over 3 is exactly the ratio of the highest coefficients. So to summarize, if px and qx are both polynomials in x of the same degree, same degree in x. So for instance, px is an xn plus an minus 1 xn minus 1, etc., etc. This is the last term, a1 x plus a0. Now qn is bn x to the power n plus bn minus 1 x to the n minus 1, etc., etc., plus b1 x plus b0. Then limit x approaches infinity, px over qx. This will be equal to the highest coefficients, an over bn. So here we assume an and bn, they are non-zero, an non-zero. Bn non-zero. So this is the highest leading coefficients. The leading coefficients. Ratio of the leading coefficients. So this is the ratio of leading coefficients. So this is only true if they have the same degree. Okay, this is only true if they have the same degree. Okay, they have the same degree. So we can find the leading coefficients. Okay, for instance, example. Limit x approaches infinity, 3x cubed plus 5x squared plus 2x plus 1 maybe over 6x cubed plus 2x squared plus x plus 1. You know, this limit x approaches infinity. So you see denominator and numerator, they are both polynomials in x. Okay, they are the same degree. They are both degree 3. Okay, polynomial in x in degree 3. Then you see they have the same degree. So in this case, what we do is so this limit is actually, we get the conclusion. This is actually 3/6 is the 1/2. Okay, 1/2. Okay, how did we get that? We divide by the highest degree. Okay, we divide by the highest degree. Every term divided by x cubed. Everything divided by x cubed. Everything divided by x cubed. Now, the numerator will be 3/5/x. Use power rule, okay? 2/x squared plus 1/x cubed over 6, 2/x, 1/x squared, 1/x cubed. And you see the lower degree, the coefficients of the lower degree, you know, when we divide by the highest degree, then they should have some factor of x in the denominator. And then numerator has no factor of x. Numerator is finite. Denominator can be absolutely large. So these terms, as x approaches infinity, they all approaches 0. So we get a 3 plus 0 plus 0 plus 0 over 6 plus 0 plus 0 plus 0. You see, only the leading coefficients remains. Okay, the leading coefficients remain there. So we get the ratio of the leading coefficients. Okay, so we get the ratio of the leading coefficients. Then we are done. Okay, then we are done. Okay, so this is the this limit. Okay, more examples. Example. Now, if so let's see, x squared plus 1 over x, limit x approaches infinity. Okay, now x squared plus 1 over x. Now if you write in this term, split terms, this is x over 1 over x. Okay, now you see, as x becomes ultra large, so we have factor of x. We have term x. We have term 1 over x. 1 over x is bounded as x approaches infinity. It approaches 0. But x, actually the term x approaches infinity. So this is actually infinity. This is infinity. Now in general, if px over qx limit x approaches infinity, this is the infinity. If degree of px greater than degree of qx. Okay, degree of p is greater than degree q, then we get infinity. Now if degree p less than degree q, then actually we get 0. If degree p is less than degree of q. Okay, so for instance, limit x over x squared plus 1 limit x approaches infinity. This will be 0. Okay, this will be 0 because small degree, small lower degree is controlled, is dominated by higher degree. Okay, higher degree. So if you do the algebra, so this is x approaches infinity, divide by the highest power, every term. Okay, so this will be 1 over x. This will be 1 over x squared. Limit x approaches infinity. Now, as x approaches infinity, y over x approaches 0. Okay, this approaches 0. This is approaches 0. So this is 0 over y. So this will get a 0. Okay. Okay. Another property. Let's, for instance, okay. Now you see, denominator is degree 2. Numerator. So what's the essential degree of numerator? Now numerator has a factor x to the power 4, but it's within the square root. Okay, so it's essentially of around degree 2. Okay, it's degree 2. So we divide by the highest power, degree 2. So this is actually equal to limit x approaches infinity divided by degree 2. The highest power is degree 2. Now this degree 2, we divide by x squared. Now x squared we can write as square root of x power 4. Okay, this is square root of x power 4. X squared over x squared is 1. Don't forget this limit notation. Okay, now we use the property of square root a over square root b equals square root a over b. Okay, and then we use this property, then we get the numerator will become, so this is the square root of x power 4 over, and then split the factors. So this we get x power 4 over x power 4 plus 1 over x power 4 over 1 over 2 over x power 2. Now, then we take limit. This x power 4 over x power 4, this is 1. Now this limit, now distributed thing inside. Now finite number, 1 or 2 over x to some positive power. The limit is actually 0. 1 plus 0, this is square root of 1 plus 0. So this is the 1 over 1, which is we get a 1. So we have horizontal asymptote. Which is y equals to the value. Okay, y equals to the value. Y equals to 1. Okay, so this is the infinite limit. Now let's do a summary of curve sketching. Summary of curve sketching. Okay. Curve sketching. Of curve sketching. Okay. When we sketch a curve, what kind of property do we need to to plot, to keep in mind? Some key property of a curve you need is the following. First, domain. Okay. i.e. the x values such that the function is defined. And then b, special points, the intercepts. Okay, x1 intercepts. Okay, i.e. Do we have the intersection with x, y axis, intersections with x axis and y axis. Okay, now then the third thing is symmetry. Now use symmetry, we can reduce work. Okay, for instance, if even function, so suppose if we have even function, so even function is function that satisfies f negative x equals to x for all x in the domain of x, in the domain of D, in the domain of F. I.e., the function value are the same if you plug in x or negative x. Okay. Okay. So what is examples? What are examples of even functions? Anyone know any examples? Even functions. Okay, even functions, we have a lot of examples. For instance, y equal x squared, y equal x power 4. Now, as long as we have even powers. Okay, for instance, we have cosine x. Okay, cosine x is, even. So even functions are symmetric. Even functions are symmetric. Even functions are symmetric with respect to the y-axis. Y-axis. The examples that we gave. So for instance, so example, y equal x squared. So it's y equal x squared. You see, this is symmetric with respect to y-axis. Okay, symmetric. With respect to y-axis. Now cosine x. Y equal cosine x. You see cosine x. Okay. So this is the x, this is the y. Y equal cosine x. Now again, it's symmetric with respect to y-axis. So if we know a function is even, then actually we only need to plot half of its graph. Okay, and then the other half follows by symmetry. So we just flip by symmetry with respect to the y-axis. Then we get the other piece. Okay, all the functions. What are all the functions? All the functions are functions that satisfies the property that f negative x equals negative fx. Okay, for all x. Here for all x in the domain of f. Now examples. Examples are, for instance, any odd powers of of course, y equal fx equal to x. Now, etc. Also, for instance, sine x, tangent x, they are both odd. Cosine x, they are both odd functions. Now, fact is, all the functions, the graph of all the functions, graphs of all functions are symmetric with respect to the origin O. Okay. For instance, of course, x to the negative 1. This is also all the power of x. Now it's symmetric with respect to the origin O. I.e., you see, if we have any point here, for instance, this is P, then you see, by symmetry with respect to origin O, then we have P prime. Okay. Now suppose we have point Q. Now by symmetric with respect to origin O. Okay, this is O. Now we have a point on the other pieces, Q prime. Okay, Q prime. Okay. So it's symmetric with respect to O, origin O. Okay, so we just plot one pieces and then the other pieces follows again by symmetry. So this can also reduce work. This can also reduce work. Okay. And other factors including asymptotes. Now, what we usually do asymptotes is horizontal asymptotes or vertical asymptotes. Horizontal or vertical asymptotes. A function can sometimes have an asymptote that is neither vertical or horizontal. In this case, we call it a slant asymptote. Okay. But you need to keep in mind, sometimes we can have this situation. What we usually do is horizontal asymptote, horizontal or vertical asymptotes. Okay, horizontal asymptotes or vertical asymptotes. Sometimes we have slant asymptotes, but it's not required. Okay, i.e. we need to find whether we have this kind of limit fx approaches x. So look at the limit behavior fx, limit behavior of the function value fx as x approaches negative infinity or positive infinity. Whether they have limit, okay, whether they have limit or not, or whether we have infinite limit as x approaches a from left, or plus minus infinity, or x approaches a from right, okay, plus minus infinity, etc. In these cases, for instance, if this L1, L2, if this limit have this kind of situation, this limits, then we have in the first two cases, these two cases, we have a horizontal. Horizontal means x approaches infinity, okay? X is the horizontal, okay? X value approaches infinity. Y value, fx, get an object close. The function value get an object close to number L, okay? I.e., the function is around, near stable, okay? Stable around one number. So it's a horizontal, okay? It does not change, no fluctuation. So it's horizontal asymptote. Now, vertical is the second two cases. We have vertical asymptotes. The third case, slant asymptotes, we will no longer talk about. We will not give examples of that. Okay. And then other properties are the increasing and decreasing. So the increasing interval of increases or decreases. Intervals of decreases, of increase or decreases. I.e., the thing that we do is use increasing decreasing test, find increasing decreasing test. Okay, what we do is increasing decreasing test, find decreasing test. So we need to determine f derivative of x is positive or not, or f derivative is less than 0. Okay. For what values of x such that derivative is positive, and for what value of x derivative is negative. Okay, find all such x values, and then we can totally determine when the function is increasing or decreasing. Okay, increasing, decreasing. Then from increasing, decreasing, intervals of increasing and decreasing, then we can find some key property, i.e. local max, local min, local max, local min, local max, local min, local max, and local min. We can use first derivative test, okay? I.e. the function is increasing then decreasing, okay? Increasing and then decreasing. So increasing, decreasing. So this we get local max. Now decreasing and then increasing. So we have local min, local min. Okay, local max, local min. And then concavity, 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 concavity. So we use concavity test. Concavity test. Concavity test to determine its concavity. Okay, in concavity and inflection points. Inflection points is a point. An inflection point is a point on the curve such that the concavity changes. Okay, i.e. the function changes from being concave up to being concave down. Okay, or change from concave down to concave up. So we have inflection points. Inflection points. Then this is around the key properties. This is probably including the most important key property of a graph. Then we try to combine all the pieces of a function and then plot. Okay, combine all the pieces of information and then plot. Combine all pieces of information and then plot. Last step, sketch the graph. Sketch the curve. Sketch the curve. Sketch the curve. Now today we no longer have enough time to give you examples. Next week we will actually do examples how to plot curves given given explicit expression how to plot curves. Now the remaining time we will have a quiz. Okay, we will have a quiz. Now this quiz, you know, we will actually allow you can use your book, use your notes. Okay, you can use your book and your notes.